अपने स्टूडेंट्स एंड तलबा से कहूँगा कि वो इस मुल्क का एक बहुत बड़ा असेट है और उन्हीं को आगे चल के इस मुल्क की बागडोर संभालना है।
हेलो एक्सीलेंस।
What is excellence?
Excellence isn't something that happens overnight, but it's a gradual process.
Excellence is not a destination, it is a journey, and we pursue excellence every day in our lives.
Here at Integral University, we understand that every person is excellent in their own unique way, and hence we devise programs to bring out their excellence.
Imagine an engineer who can build a wall with his or her own hands. Imagine a person who just graduated and knows how to fix a bicycle or a motorcycle for that matter. Such is the skilling that our university believes in imparting to our students.
Excellence does not only means advancement in education but also becoming socially and emotionally mature enough to face the life and facing oneself.
Hello Excellence.
The hands-on training imparted through our agile curriculum and imparted by our faculty with considerable industrial experience in the manufacturing, corporate, agriculture, law, medical and architecture fields, for example, allow our students to start delivering value to their employees and employers immediately.
At Integral University, pursuit of excellence is full of happiness, knowledge, friends, teachers, and yes, last but not the least, dreams.
Excellence is when you gather new knowledge every day.
Excellence is when you stay focused.
Excellence for me is setting a goal and achieve it.
That is the excellence we are targeting.
Hello Excellence.
Hello Excellence.
Hello Excellence.
Hello Excellence.
Hello Excellence.
Learn,
Grow,
smile and keep going.
Welcome to the world of excellence.
Integral University, Lucknow. Inspiring excellence.
A very good afternoon to all the dignitaries, faculty members and their participants. On behalf of Department of Commerce and Business Management, I, Dr. Zain Mendi, Assistant Professor, Integral University, feel honored to moderate this session virtually among such esteemed audience and welcome all of you to the 9th day of 2-week online quality improvement program on research methodology and data analysis organized by Faculty of Commerce and Management in association with Faculty of Doctoral Studies and Research, Integral University, Lucknow. The topic of today's session is non-parametric test, which is used for research data analysis. It is also known as distribution-free test because they are based on fewer assumptions, that is, they do not assume that the outcome is approximately normally distributed. Commonly used non-parametric tests are Wilcoxon signed rank test, Friedman test, Kruskal-Wallis test, Mann-Whitney test, ANOVA, and chi-square. Milton Friedman rightly said, statistics do not speak for themselves. With these words, may I request Professor A.K. Saxena, Dean, Faculty of Commerce and Management, Integral University, to express his opening remarks of the session. Welcome, sir.
Thank you. Good afternoon, everyone, particularly the key expert speaker of the day, Professor Ajay Kumar Chauhan from the Research Shiksha, New Delhi. It is indeed a matter of great pleasure and pride for us that we have entered in the 9th day of the QIP, which we are organizing since August 26th, July 26th, on the research methodology and the data analysis. In the same sequence, today we have invited one of the learned authority expert in this field. I personally, on behalf of the Chancellor, on behalf of our Pro-Chancellor, Vice Chancellor, Pro-Vice Chancellor, Dean Doctoral Study, Dean Research Development, and on behalf of the Department of Commerce and Business Management and my personal behalf, I welcome you. And interestingly, Professor Chauhan is going to talk on all foreign tests. The names are so foreign, so it is giving you another flair. Yesterday we had test, which was on a parametric test, and today he's going to talk and speak on the non-parametric test. Well, it's very important and pertinent to make a mention at this point that the formulation and consequent testing of hypothesis, which is a vital part of any research project, has got majorly two types of tests: the parametric test and the non-parametric test. The parametric test, they are quite good number, but t-test, f-test, z-test, and others are there. In non-parametric test, as rightly pointed out mentioned by the moderator, Dr. Zan, he shall be talking on Wilcoxon's sign rank test, Feynman test, Bruxelles Wallis test, and man witness test, along with ANOVA and the chi-square. In our times, chi-square, regression, and correlation were the three very important tests which serves and suffice to purpose of any quantitative technique analysis. But now these tests have come up. This is called research. That's why we said testing and retesting of the hypothesis is called research. It is not what has happened. If that would have been the case, the researcher would have not gone forward and talk about which Mr. Chauhan is going to talk today. We would have been restricted ourselves to the correlation, regression, and chi-square, at the most ANOVA. Even people serve their purpose of research analysis, data analysis with the mean, median, mode, association of attributes, and so on and so forth. With this opening remark, I'm pretty confident that Professor Chauhan is going to include all these aspects which has been interestingly chosen to speak to all of us. And the participants, who are majorly the research scholars and the teachers of the department, and throughout the country, our research scholars are scattered, who are doing PhD from here. It's not only confined to the research scholars of the Department of Commerce and Business Management. This is the scholars of all the disciplines, and we have got 27 departments here with 11 disciplines, 11 faculties. Exclusive is the medicine faculty is still there. With this opening remark, I would request Dr. Zain Mehndi to kindly invite the learned expert to give his talk and deliver the lecture on the topic which we have already mentioned. Thank you very much.
Thank you, sir. Thank you so much, sir, for your words of wisdom. Now, I would like to welcome and introduce our eminent speaker of today's session, Professor Ajay Kumar Chauhan, who is presently serving at Research Shiksha, New Delhi. Professor Ajay is working as an independent consultant of quantitative methods. He is also working as a visiting faculty with various top B schools, that is MDI, IMT, NM, IMS, IIFT, and many more. He has published more than 25 international research papers and 3 books. Along with this, he is a well-known trainer of data science and analysis. He has conducted more than 500 national and international training workshops on topics such as financial econometrics, time series analysis, structural equation modeling, and others. Once again, most welcome, sir, to this session and their queries in the chat box during the session. Now, over to you, sir. Over to you, sir.
Okay. Good afternoon to all of you. The topic on which I am going to speak today, the non-parametric test. And I have a experience about the parametric and non-parametric test that the scholars are having a lot of confusion between the two types. Okay. So first of all, I want to tell you the meaning of parametric so that you can understand when it is non-parametric. There is a concept in research. This concept is known as statistical inference. The meaning of statistical inference is when you conducted a test on the sample and examine or do some hypothesis testing, and you are doing the hypothesis testing on the sample data. So I am asking you a very simple question. The results of the hypothesis testing is applicable on the sample or it is applicable on the population. So what is the purpose of doing the hypothesis testing on a sample? And I hope you are guessing it, but I am telling you the right answer. So whenever we do the hypothesis testing on a sample, the conclusion should be made on the population. Like for example, if you are making a dish, vegetable or rice or something in your home, and if you give a sample to the person to taste, so whatever he will say to you is not for the sample. So he will say about the whole dish, right? For example, if you go to a sweet shop and ask the shopkeeper that I want to taste this sweet, so he will give a small piece to you for tasting, and after tasting it, you have to decide on the population, not on the sample, right? So this is the basic concept of the parametric, that we do the testing on the sample, but conclusions are made on hypothesis or population. So this is the concept of parametric. So in parametric, the conclusion are made on the population, not on the sample. So parameter means something which is related to the population. Now in many cases, what happens that you are doing a test for the sample, but cannot conclude for the population. So it means your conclusions are not applicable on the population. This is one problem that we have in the non-parametric. So parametric means you can generalize the results. Non-parametric means you cannot generalize the results. So this is the broad classification between the parametric and non-parametric. Okay, so I hope you understand what is the difference between parametric and non-parametric. In parametric, conclusions are made on the population. In non-parametric, we want to understand and make the conclusion on the sample. Normally, we are not 100% confident that we can make conclusions on the population. Like for example, if I go to the some city, and found that some of the people are very naughty, so I cannot say the whole city is naughty, because on the basis of very small sample, I cannot make any conclusion about the population. Now the question is that what make the difference between the population, between the parameter and the non-parameter? So how can we say that this study is parametric, this study is non-parametric? So first of all, I will tell you the 5 properties of a parametric test. You can apply the parametric test only when these 5 properties or features fulfilled. So number 1, the first requirement of a parametric test is that your data should be very large so that the distribution is normal. So why first condition of a parametric test is the normal distribution. That the variable, all the scale variables rather, you have in the data set must be normally distributed. Skewness and kurtosis should be less than 1. Skewness and kurtosis should be less than 1. So normally we test this condition whether the skewness and kurtosis are less than 1 or not. So this is the first condition. Second condition, if your you can apply the parametric test when so any 2 samples or any 2 groups within the data must have equal variance. This concept is known as equality of the variance or homogeneity of the variance. And the homogeneity of variance is examined with the help of Levene test. So we examine whether the two different samples are having equal variances or not. And one of the properties that the variances of the sample is equal to the variance of the population. But because we don't have the variance of the population, so we can't check it. The only thing that we can check is that whether the 2 samples, 2 groups in the data set are having equal variance or not. And this test is known as Levene test, and we can do it in SPSS. Normally when we compare 2 different groups or 3 different groups, like with the help of independent sample t-test or one-way ANOVA, we always check whether the samples are equal in variance or not. This is my second condition. The assumption number 3, that if you are going to apply any of the test, at least one variable should be scale variable. At least one variable should be a scale variable. If you have odd category variables, you cannot apply parametric test. If you have only nominal variables and the ordinal variables, only nominal and ordinal variables, you cannot apply parametric test. So parametric test is applicable when
the definition of applicable that concerns somebody, something relevant to somebody, something.
Hello. Yeah. So the condition number 3 is that you must have at least one scale variable to apply parametric test. The fourth condition, the condition number 4. The condition number 4 is that the sampling should be random, means the way you collect the sample should be random sampling. And the last is that the responses of different respondents should be independent. And if top 3 conditions are not fulfilled, in any of the top 3 conditions are not fulfilled, then you have to apply the non-parametric test. And now, in what circumstances we can apply? In what circumstances we can apply the non-parametric test? Number 1, when the data is not normally distributed. Okay, so I am getting messages from the organizers, and I request you to keep patience because I designed my lecture accordingly. Please be patient. So now the condition is that if you don't understand these concepts, you cannot understand non-parametric, I'm telling you. So what is the non-parametric? So once we understand the parametric, so we can easily understand the non-parametric. Non-parametric means when the condition number 1, condition number 2 and condition number 3 of parametric test is not fulfilled, then we can move to the non-parametric. So there are two special conditions when we can move to the non-parametric. Number one, when data is not normal. Number two, when you are dealing with very small samples and you are dealing with the only the scale, the ordinal variables and the nominal variables. Okay, so with this comment, I am going to share my screen and so somebody please tell whether you can see the screen or not.
Yes, sir, it is visible.
Okay, thank you. Now, non-parametric test, as I told you, is applicable in only two conditions: when your sample size is less than 30, very small, and condition number 2 is that you are having only nominal or ordinal variables. So there are four or five non-parametric tests I am going to discuss today. Number 1, chi-square test, and let me show you I write the whole chapter on this topic. This is the chapter. I write a book. So this is the chapter number 9 of the book. So I am going to cover chi-square test, which is the king of non-parametric test. The chi-square test is known as king of non-parametric test. Then we have Wilcoxon rank sum test, Mann-Whitney test, Kruskal-Wallis test, and Friedman-ANOVA test. So these 4 tests I will discuss today in this session. So these are the most demanding tests. And why we are applying these 4 tests? Because the first 3 conditions are not fulfilled. So that's why we are moving to the non-parametric test. Okay. Now, first test is chi-square test. Let me explain the chi-square test. And so I have PPT for chi-square and different examples I will share with the dataset. So first of all, in chi-square test, I want to tell you about 5 things. Number 1, where it is applicable, what is the assumption of chi-square, hypothesis, applying, application, and association. Okay. So chi-square is the most popular non-parametric test, and we are applying the chi-square by analyzing the association between the nominal variables. So when we want to find out the association between the nominal variables, we use chi-square test, and the null hypothesis of chi-square test is always written in this format, that there is no association between nominal variable 1 and nominal variable 2. So nominal variable, if you remember, it is a category variable. So category variable 1 and category variable 2. And the chi-square is also applicable between the observed and expected frequencies, and the difference between the observed and expected frequencies gives you a logic that whether the association is possible or whether the association is not possible. And if any mismatch you found between the expected and the actual, then it means some association is possible. For example, let me give you a very simple example. I give you a coin and ask you to toss at least, let's say 20 times. So I ask you to toss a coin at least 20 times. And after tossing the coin 20 times, I am asking you how many head are appeared? How many times the head was appeared? Now, in this case, if I ask this question to any layman, what answer should come? And the answer is 10. If anybody toss a coin 20 times, so at least, so on an average, the head comes 10 times out of 20. Any layman can tell me this answer. Now, I'm asking you, if you toss a coin, how many times head was appeared, and you are saying that out of 20, 15 times head was appeared. Now, my question is that so something problem with the coin. I feel there is a problem with the coin because I'm expecting only 10 heads and you are telling me 15. So it means your coin is biased. It gives more head rather than tail. Right. So in this way, we compare the actual frequency, which is 15 in your case, and expected frequency, which is 10. So whenever I compare the expected and actual, so the difference is the logic of association between the two categories. Okay, like so chi-square is having two assumptions. The chi-square test is having two assumptions. Number one, both the variables between which you are interested in finding out the relationship or association must have nominal in nature, must be nominal in nature, and every variable must have at least two different categories. For example, gender is having two different categories, male and female. So every category variable must have at least two subcategories. Like marital status is having two categories, married and unmarried, and in each subcategory, so there must be minimum frequency of 5. For example, if you make a 2 by 2 contingency table, I will tell you that what is contingency table. The expected frequencies in each case should be greater than 5. This 5 is the minimum expected number in the table. So I will tell you that what is this contingency table and what is the meaning of this 5. And whenever we apply the chi-square test, we have to design a cross tabulation first, and in the cross tabulation we have to find out that what is the frequency of different subcategories. And on the basis of my cross tabulation, I calculated the actual frequency and the expected frequencies. Let me show you this part first in the SPSS so that we can relate with the meaning of it. Okay, I start with this example. So I will tell you step by step how we can perform the chi-square test in SPSS. Okay. Now, in this case, we are having two category variables. So a company is experimenting about on the employees in order to increase their performance. So there are three experiments: experiment number 1, experiment number 2, and experiment number 3. So there are three experiments, and after doing the experiment on the three different groups, we want to find out that where the performance is the best, where the performance is average, and where the performance is poor. Or you can imagine that we are having three different groups. In one group we do the experiment 1. In second group we conducted the experiment number 2. In third group we are conducting the experiment number 3. So first of all, I am showing you how to make the cross tabulation between them. And experiment and performance I am taking in the row and column. Okay. Now the table you can see here. So this table is known as contingency table. So this table is telling you that in every group there are 30 participants, and out of the 30 participants where we conducted the experiment number 1, 20 is showing best performance, 5 is showing average performance, and 5 is showing poor performance. Now I'm asking you, how many cells are there in this data, in this table? 1, 2, 3, 4, 5, 6, 7, 8, 9. Why 9? Because this is 3 by 3 table. So there are 3 subcategories in the variable number 1. There are 3 subcategories in the variable number 2. Don't include the total into it. So this is a 3 by 3 matrix, and number of cell is 9. So more than 80% of the cell must have the frequency more than 5. So there is only one cell where the frequency is less than 5. So that is fine, no problem at all. More than 80% of the cell must have the frequency more than 5. So this is the meaning of, I write here second part, you just read it. In the 2 by 2 table, the expected frequency in each case should be greater than 5. In larger contingency tables, the rule is that all expected count should be greater than 1, and no more than 20% of the expected count should be less than 1. Or in other words, 80% of the cell must have the frequency more than 5. So I write this here, 80% of the expected cell count is greater than 5. Okay. Now after that, the frequency is observed frequency. From observed frequency, we calculate this expected frequency. We also calculate expected frequency by using this formula. And let me show you the expected frequency also here. If I go to the analyze, descriptive, cross tab, and go to cell, if you click on the expected frequency, so you can also see that 11 is expected, 20 is actual, 9.7 is expected, and 5 is actual. So we are having the expected frequencies and the actual frequencies in this table. Now this is the basic table that we are going to use in chi-square test. Okay, so how to use chi-square test? Now we apply the Pearson chi-square test on this table. Pearson chi-square test is showing you the difference between the observed and the expected. This is observed value, this is expected value, and this is expected value. So we apply this formula, and one thing by common sense you can analyze, if observed and equal are same, this value is 0 and chi-square value is also 0. So the most ideal value of chi-square is 0. The most ideal value of chi-square is 0, and larger the r-square, it means observed and the expected are different from each other. The expected and the observed values are different from each other, and more they are different, higher is the value of chi-square. So chi-square, the value will tell you that how much observed and the expected are different. And after that, the calculated value of Pearson chi-square is compared with the table value at 5% level. Degree of freedom of chi-square is rho minus 1 into column minus 1. And if the calculated value of chi-square is greater than critical value, the null hypothesis can be rejected. Okay. Now after analyzing the chi-square value, we have to find out the strength of the association. Now I want to find out that if association exists between the two variables, what is the strength of the association? So strength of the association is measured by phi value, which is applicable in 2 by 2, and in more than 2 by 2 contingency table, we apply Cramer V. So let me explain you with the help of the analysis. Now suppose I want to apply the chi-square test between the data set. So this is my data set. I have two variables. So first variable is also nominal, second variable is also nominal, and I want to examine the association between the two. So what is the complete command of chi-square? So I go to the cell, select observed and the statistics, and in the statistics I click on the chi-square and phi n Cramer. So these are the must to calculate values in chi-square test. And let's OK. So when the output comes, first of all, you have to check what is the Pearson chi-square value and its p-value. What is the p-value of chi-square? So first of all, check the value of chi-square, check the value of Pearson chi-square, and if the Pearson chi-square value is less than 0.05, it means there exists significant association between the two categories. So I repeat, if p-value of chi-square is less than 5% significant level, it means the two variables are significantly associated. Now we concluded one thing, that the chi-square is found to be significant. The variables have significant association. So once we find out that, now the second question is that whether the association is moderate, whether the association is weak, or whether the association is strong. So we have three options: strong association, moderate association, or the weak association. So normally we divide into two categories. We can't say it is a weak association, because if association is significant, it can't be weak. So either it will be moderate or it will be strong. Now we have to find out the Cramer value. If Cramer value, listen carefully, we don't check phi value in, I have not seen phi value much in use. We always prefer to quote the Cramer V. Cramer V measures the strength of the association, and if it is more than 0.5, then we can say the association is strong. If Cramer V is less than 0.5, we can say the association is moderately strong. And if it is insignificant, then we can say there is no association. So in this way, we conclude that whether the association is a strong association or whether the association is a moderate association. Now, the next is we have to check this contingency table. So why I'm checking this contingency table? Because I know that there is a significant association. The association is moderately strong. Now I want to find out where the association exists. Association, if association is there, so where is the association? Association hai kahan? So we have to find out where is the association. Now association we have to find out by comparing the actual values with the predicted values or expected values. Now my experiment 1. So in case of experiment 1, the best performance. So because we want best performance, so I'm comparing only this column. In experiment number 1, the expected best performance is 11, actually is 20. In experiment number 2, the expected best performance is 11 and actually is 10. No, not much difference. In experiment number 3, the expected best performance is 11, but actual best performance is 3. So I conclude that the experiment 1 is giving me best performance more than expected. So this is my conclusion from the chi-square test, that from all the tables, my conclusion is that the experiment number 1 is giving me best performance, which is more than expected, because we are expecting 11 and the actual is 20. So there are 3 conclusions of the chi-square test. Number 1, whether the association between the variables is significant or not. Number 2, what is the strength of the association, and number 3, where is the association. So if you answer 3 questions, it means your chi-square is complete. So for practice, I'm doing one more exercise. Let's see this. Okay. So here first of all, I'm explaining you the data. Now this is a easy example. So the example is that the employees of a company are divided into 2 groups. First group is sending to the health camp for attending the lectures. The second group is sent to listen the awareness lecture. So we are having 2 groups. One group is sent to attend the health camps, and the second group is sent to listening the lectures. Okay. Now after 1 month, the company asks that, do you feel any improvement in your health? 0 if yes, 1 means no. Now I want to know, is there any association between the type of treatment and the improvement of the employees? So I am interested in finding out the association between the 2 variables. Both the variables are nominal in nature. So I am going to compare the descriptive, cross tab, 1 variable in the row, 1 variable in the column, statistics, chi-square, and for chi-square, and phi and Kramer is for analyzing the strength of the association. Then we go to the cells. I want to compare observed and expected. Continue and OK. Now my first question is that, is the association significant? The answer is yes. Why? Because Pearson chi-square value and all other tests showing me significant p-value. So my first question is that, is the association significant? Answer is yes. My second question is, what is the strength of association? The answer is, it is moderately strong, because 0.356 is representing that there exists moderately strong association between the 2 categories. Then my third question is, where is the association? If association exists, where is the association? Now my answer is that who improve health camp, expected improvement is 14.4, actual improvement is 28. Awareness lecture, so the expected improvement is 61.6 and actual is 48. So my conclusion is that health camp leads to better health improvement. So my conclusion from this exercise is that the health camp leads to better health improvement of the employees. So in this way, we can run chi-square test. So I hope you understand chi-square test. Now we are moving to the next test. Now, before moving to the next test, I want to explain you the concept of rank. Because all the tests which I am going to explain you, Wilcoxon, Mann-Whitney, Kruskal, and Friedman. So all the 4 tests like Wilcoxon, Mann-Whitney, Kruskal, Friedman, all the 4 tests actually depends upon the rank system. Now we have to understand what is the meaning of rank. So first of all, I am going to show you what is the meaning of rank. So this is a data set, and we will use this data set for the Mann-Whitney test. Okay. Now, before going to the next, I'm just going to show you how ranking is performed. Like, for example, I'm saying that these are some of the numbers, and I want to convert these number into rank. So this is the number, and this is the rank, right? Okay. See, the lowest number is 2. So I will give this rank number to 1. So 3 comes 2 times, 1 and 2. So it means they come on second and third position. So their rank is 2.5 and 2.5. They will share the equal rank because they are holding the position second and third. So the average of second and third is 2.5. So I put 2.5, 2.5. Similarly, 4 comes 3 times and it's hold the position of 4, 5, 6. 4, 5, 6. So I put 5, 5, 5 because the average of 4, 5, 6 is 5, 6. Then we are having 7th and 8th position. So 7.5 and 7.5. So in this way, we can convert the numbers into rank. And if you don't understand the ranking system, you cannot understand any of the non-parametric tests I'm telling you. So you have to understand what is the concept of rank. So I'm giving you one more example. Like in this case, in the yellow portion, or okay, actually we calculate the combined rank. So we are having 2 groups here. One is pre and second is post. In pre group, there are 20 people. There are 20 people in the pre group, and I'm calculating the rank of each. So you can see that the highest number is 20 and 20 and okay, highest number is 35, or the lowest number, I think the lowest number is 13. So 13 is the lowest number. So 13 and 13 comes 2 times, 13 and 13. So they are holding the position of 1 and 2. The half of 1 and 2 is 1.5, 1.5. So all the non-parametric tests, whether the Mann-Whitney, Wilcoxon or any other Kruskal-Wallis, Stratman, ANOVA, all the 4 tests are based on ranking system, and they will applicable on the rank, not on the number. They are applicable on the rank. So you have to understand the meaning of rank. Now we are going to start the Mann-Whitney first. So first of all, I am going to explain you the concept of Mann-Whitney. Now what is there are 4 tests, and all the 4 tests are the inferior substitutes of parametric test. Like Mann-Whitney is the inferior substitute of independent sample t-test. Mann-Whitney is the Wilcoxon test is the substitute of paired sample t-test. Kruskal-Wallis is the substitute of repeated sample one-way ANOVA, and Friedman test is the substitute of one-way ANOVA. So all the 4 tests are basically the substitutes of different tests. So first of all, I am going to explain a Mann-Whitney test. Okay, so let me open the data first. So there are many Mann-Whitney tests. Okay, let me try this. Okay, so this data set I took from the Andy Field book. So in this data set, you can see carefully, there are 20 people. There are 20 patients. And these 20 patients are suffering from the depression. So BDI is a measure of depression. Their depression level is measured on Sunday initially. Then to the first group some drug is applied. So their doctor give the drug to these 10 people, and to the next 10 people they provide only the alcohol. No drug, only the alcohol. So on Sunday, their depression level is examined. After that, doctor provided them the drug and the alcohol, and after 3 days, their depression level is also measured. So this is an experimental design, and in this experimental design, we want to know that which is more effective, the drug or the alcohol. So we have to find out that which is more effective. Okay, now I am telling you the mechanism of this example. So first of all, I am going to the, I am taking this data, and let me open the Excel file. Because if you don't understand this mechanism, understanding the non-parametric test is just impossible. So this is my data set, and so the first group to whom doctor provide drug, I am covering with the yellow, and the other category to whom the doctor is providing the alcohol, I am shading with a different other color, this. So this is our data set. Now the question is that how to apply the Mann-Whitney test on this data set. So I am explaining you the concept. Okay. So the first is I am calculating the rank. This is Sunday, depression level of Sunday, and this is the depression level on Wednesday. So I am calculating the rank on Sunday. And after that, I will calculate the rank on Wednesday. Okay, so how to calculate the rank? This is the treatment or experiment EXPT. Let me write EXPT, and this is my serial number. Now, how it is easy to find out the rank, and I'm telling you, I just sort these values in ascending order, smallest to largest. Okay, now I arrange this data into ascending order, so that I can give the rank very quickly. 13 it means 1.5 and 1.5. So the position is exactly 1 and 2. Then 14 is 3, 15. So they are holding the position in 4, 5, 6. So I can give 5, 5, 5, because 15 are holding the position 4, 5, 6. So the average of 4, 5, 6 is 5, 5, 5. So then we are having 4, 5, 6, 7, 8, 9, 10. 7, 8, 9, 10. So the average of 7, 8, 9, 10 is 8.5. So I am giving 8.5, 8.5, 8.5, 8.5. So the actual position is 6, 7, 8, 9, 10. So 10 up to 10th we already provided the rank. Then this is the 11th. This is 12, 13, 14. It means 13. So we provide the equal rank. In fact, they are 12, 13, 14. 15, 16, 15.5 and 15.5. Similarly, we can give rank to the 2020, which is 17, 18, 17.5 and 17.5. Finally, we have the rank 19th rank and the 20th rank. So in this way, we provide the rank. Now I'm giving the rank to the Wednesday. First of all, arrange into smallest to the highest. Now you can see how I am providing the rank. First, 2, 3, 4, 3.5, 3.5, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, now we are having 16, 17, 18 have the same rank. So 17, 17 and 17. And this is 19 and 20, 19 and 20. So this is as easy to provide the ranks. Now I arrange all the data set in previous order. Okay, now we arrive in the beginning. So we have this data set. This is my yellow color. Okay, now I am calculating what? See this clearly. So I am calculating the mean rank of group 1 on Sunday. Similarly, mean rank of group number 2 on Sunday. So what is the mean? So I am calculating the average. If I take the average of this part only, you can see. So this is the average of the rank of the group number 1 on Sunday. Similarly, if I take the average of this, so I am calculating the average of the mean rank of the rank of group number 2 on Sunday. So this is mean rank on Sunday. So let me remove this. I just calculate the mean rank of group number 1, mean rank of group number 2, and now I am calculating the mean rank on Wednesday. And I just copy and paste because it is referencing. Referencing wheel is working here. So this is our answer. Okay. So I am now I am asking you, can we say the mean rank of the two groups on Sunday are same? Or can we say the mean group or of the mean rank of the two groups on Wednesday are same? So this answer we will get from the Mann-Whitney formula. So what is Mann-Whitney formula? The Mann-Whitney perform a formula. So answer, I'm showing you the formula, Mann-Whitney. Yeah. So this is the Mann-Whitney formula, N1, N2, N1 plus N2, this is the formula. And now because we are going to do it in SPSS, so I'm showing you in SPSS. So first of all, I show you manually, and now I'm showing you on SPSS so that you can relate the things. Okay, so I am applying the analyze non-parametric test, and you can see that I clicked on two independent samples because Mann-Whitney is the substitute of t-test, independent sample t-test. So I am taking the two values, Sunday and Wednesday, comparing the drug, and in drug I'm giving 1 and 2. 1 means drug and 2 means alcohol, and click OK. Now see this. On the Sunday, the average rank is 11.95 and 9.05. So I am showing you 11.95 and 9.05, right? So the software actually, the whole non-parametric family depends upon the rank system. If you understand the rank system, the non-parametric tests are easy to understand. Okay, now let's see the results. So you can see on Sunday, the mean rank of group number 1 is 11.95. The mean rank of alcohol is 9.05. Now the question is that are they same? Are they same? So Sunday I have to check the p value and z value. So this value I have to check. Now z value say it is minus 1.105 and p value is 0.269. So you know that whenever the p value is more than 0.05, we can accept the null hypothesis that there is no difference. So my conclusion is that on Sunday, the depression level of both the groups are equal. So now my conclusion is that on Sunday, both the groups are equally depressed. Now my next question is, so what happens on the Wednesday? So in the Wednesday, the mean rank of first group is 15. So the group which we provided the drug is having the mean rank of 15.1, and the mean rank of the second group is 5.9. So now we can find out the difference. Now the software say that the mean rank of the drug group is 15.1 and the alcohol group is 5.9. It means alcohol is more effective than drug in reducing the depression. Now another question is that is the difference significant? Is this difference significant? Answer is yes. Why yes? Because p value is found to be significant. So you can see the probability value is found to be significant. It means the alcohol. Now what is my conclusion? Conclusion is that the alcohol is more effective in reducing the depression, but don't take it seriously because this example is only given in the book. It is not published in any research paper. So, but according to the data set, because the data set I downloaded from the world most famous book on SPSS, Andy Field. So according to the data, the alcohol is more effective in reducing the depression. Okay, I hope you got a sense. Now I'm telling you one more example because for each test I will conduct two examples. Let me check for this experiment. Okay, this is a similar example. Okay, now let's see this. This is also an experimental design, and in this example, you are having two samples, and both the groups are having only 10 people. Sample size is very small. So whenever we are having sample size less than 30, we can't apply parametric test. And we are moving to the non-parametric test due to the small size of the samples. And we are having two groups. In first group, we are not doing any experiment. In the second group, we are doing the experiment. And so first we conducted the performance before the training, before providing you the experiment. And after the experiment, we again measure their post performance. So why we do pre-performance? To check whether they are same or not. And why we measure post performance? Because we want to check whether the experiment is significant in improving the performance or not. So now I go to the non-parametric test. And this is one sample test, two independent sample test. Pre-performance goes here, post-performance, experiment comes here. In experiment, we assign 1 and 2 because we always assign 1 and 2 to the groups, and okay. Now, if you check the pre-performance, the p-value is more than 0.05. Significance two-tailed. This is 0.195. It is more than 0.05. So we can say there is no difference. It means initially both the groups are equal. And what happens after giving the experiment? So after the experiment, this p-value, you can see it is significant, and the experiment group is having the more rank. So the mean rank of the experimental group is higher. So we can say the experiment is highly significant in giving you the performance or increasing the performance of the employees. So this is the two examples of man-Whitney test. So I hope the man-Whitney is clear. So what is man-Whitney? Man-Whitney is the inferior substitute of conducting the independent sample t-test. So I am showing you the basic definition of man-Whitney. Okay, so I am. So this is the command. This is the formula. Okay, so man-Whitney starts from here. So you have to see only this thing. When we want to test difference between two conditions and different participants, we have two choices. Man-Whitney is the first choice, and Wilcoxon is the second choice. Now I'm coming to the Wilcoxon test. So point number 1. This is the Wilcoxon test. You have to write down this command, this line. The Wilcoxon test is the inferior substitute of paired sample t-test. Wilcoxon test is the substitute of paired sample t-test. And what is paired sample t-test? When your groups are same, when your participants are same, and data is collected at two different point of time, like before advertisement, after advertisement, before training program, after training program. So there are two different time periods when the data is collected, but data is collected from the same participants. Like for example, if a faculty teaches a class of MBA students, so there are two feedbacks. Number 1, mid-session feedback and post-session feedback. Mid-session feedback means after completing 50% of the sessions, you took a feedback, and you took another feedback after completing the course. So we want to check whether the mid-session feedback is equal to the post-session feedback, and in this case, we are taking the feedback for the same faculty and from the same set of students. So then we can apply the Wilcoxon test. Let me show you. Okay, so there are 20 students in a class, and you can see that 20 student is same in feedback 1 and feedback 2. So this is feedback for faculty A and this is feedback for faculty B. You can understand like this. Let me write here. This is the feedback of X subject, and this is the feedback of Y subject. So there are two subjects, and the students are same in both the subjects, and they are providing the feedback for X as well as Y, and we want to know whether the feedback of X subject is equal to the feedback of Y subject or not. So what is important in this case? Important is that the group who is providing you the feedback is same. Right. So this is another example of paired sample t-test, because we are having the pair. So there are two type of pair, pre and post, and the also two different feedbacks. So let me apply the Wilcoxon test to it. Now you can see that I am clicking on two related samples. Okay. So the pair is feedback X and feedback Y. It is a pair. Applying Wilcoxon test. Just click OK. Now the software is saying that, Wilcoxon is saying that the average rank of the feedback Y and feedback X is 5.5 and 11.75. So we compare with the help of rank. Now in this case, actually the software do one thing. The software calculate the difference between X and Y. You can see that there is a difference between feedback X minus feedback Y, and after that we rank them. So it is found that 4 ranks are negative and 16 ranks are positive. So in 16 times the feedback of Y is greater than X, and 4 times the feedback of Y is less than X. So we can say that the positive ranks are more than the negative ranks. If they're equal, it means there is no difference. But if the number of positive ranks is significantly different from the number of negative ranks, then we can say the relationship could be there. Now, what relationship is found significant? You can see that it is a significant. 0.002 means less than 5% level of significance. So it means the feedback of Y is significantly higher than the feedback of X. So this is the conclusion we can conclude. So the conclusion is that the feedback of Y is more than the feedback of X. Why? Because the number of positive ranks are higher. Okay, let me show you one more example. So I am taking the example of in the paired sample t-test. So this is also a paired sample t-test, and I'm saving in the Wilcoxon file. The reason is that wherever you can apply paired sample t-test, you can also apply the Wilcoxon test. Now in this case, we are having 20 people, 20 women. Actually, these are the 20 women, and the data is collected from them. That what is the life quality before joining the self-help group, and what is the life quality after joining the self-help group. Now we want to check whether the joining the self-help group increases the life quality or not. So whether after joining the self-help group the quality of women increases or not. So again, I'm going to the non-parametric test, legacy dialog, 2 related samples because it is paired sample, and I'm taking the pair here. Okay. Now you just see the positive ranks. All the 20 ranks are positive. All the 20 ranks are positive. So we can say the joining of the self-help group significantly increases the life quality of the women. The conclusion is very clear because all the ranks are positive. And let me show you one thing. If I convert any rank, for example, if I am making it 76 and it is 58, so after that 58 minus 76 will be negative, and you will see different result. Two related sample, and now you can see that 19 times for 19 women the rank is positive. For one woman the rank is negative, but it is significant. But because the p-value is significant, it means we can say joining the self-help group will have a significant effect on the life quality of a woman. So this is the inferior substitute. So Wilcoxon is the inferior substitute of paired sample t-test. Mann-Whitney is the inferior substitute of independent sample t-test, and Wilcoxon test is the inferior substitute of paired sample t-test. So now I hope you understand what is the difference between Mann-Whitney and the Wilcoxon. After that, we are moving to the next, that is Kruskal-Wallis. So let me take you to the Kruskal-Wallis page. Yeah. The third test we are going to perform, the third non-parametric test, thirdly fourth. This is the fourth non-parametric test we are going to perform today. And it is the alternative of one-way ANOVA, one-way independent ANOVA. One-way independent ANOVA means all the groups are independent and they are different. So Kruskal-Wallis is another useful non-parametric test. It is used to test the difference between more than two independent samples. The test is an alternative to one-way ANOVA if the assumptions of parametric tests are validated. The Kruskal-Wallis test is based on the rank. Okay, this is the formula. Now I am showing you two examples of conducting the Kruskal-Wallis. So first thing you need to understand is that the Kruskal-Wallis is the inferior substitute of one-way ANOVA test. Okay. So let me show you one example. Yeah. So we are having two variables here. Okay. And so this is just the income. So 1 means less than 5 lakh per annum. 2 means 5 to 10 lakh per annum. 3 means 10 to 15 lakhs per annum. So the income variable is actually nominal. It is a category variable. And the second variable is a scale. That how many times they consulted the doctor in a month. How many times they consulted the doctor in a month. So we want to check the one-way ANOVA between income group and consulted group. For example, if I calculate the ANOVA test, it is a non-parametric test, but I am just showing you the method and want to check whether it is significant. Okay, now because one of the assumption of one-way ANOVA is homogeneity of variance test. You can see that homogeneity of variance test, and I calculated the homogeneity of variance test, and you can see that all these are significant. All these significant values show p-value less than 0.05. It means my assumption of parametric test is violated. So when the assumption of parametric test is violated, I have to go for non-parametric test. So now I decided to go to the non-parametric test. So this is the condition for applying Kruskal-Wallis test, that I have k groups, all the groups are independent, all the groups are different, and I want to check in this case who consulted doctor more. Are they different with respect to their income group? Income group comes here. So we are having 5 groups. We are having the 5 groups, and we want to compare how many times they are consulted doctor, whether they are significantly different or not. And Kruskal-Wallis is the test. Okay, now you can see that the software is calculating the rank of each group. The software calculated the rank of each group, and the rank of more than 20 lakhs per annum is highest. The average rank of this person or the persons, the correspondent having income more than 20 lakhs per annum is highest. So it means the p-value is found to be highest. So we can say that anybody whose income is more than 20 lakhs, they consulted the doctor maximum, followed by the people who belong to 15 to 20 lakh per annum, and after that all three are equal. After that all three are equal. So we have two significantly different concepts here. So anybody who is having income more than 20 lakhs will consult doctor more than others. So this is the answer of Kruskal-Wallis test. So let me explain you one more example. Okay. Now we divided the customer into 4 categories. Those who don't eat soya meal in the week. This is the first group, and these first group indicate the people, the patients or the respondent who don't eat soya meal. Then we have another group who they take 1 soya meal per week. Then third group who take 4 soya meal per week, and the fourth group who which takes soya meal 7 soya meal per week. Now we want to check whether the increase in weight is different in different cases or not. Now first of all, I want to apply one ANOVA, and okay, this is my category variable, and I'm examining the assumption of non-parametric test, whether it is fulfilled or not. And the software is saying that the assumption is not fulfilled. So you can see carefully that the p-value of homogeneity of variance test is not satisfied. So this is one of the reasons of going to non-parametric test. So we are not applying the parametric test here because assumption is not fulfilled. Rather, we have to go for non-parametric test. So this is the command for Kruskal-Wallis test, and number of soya is the group, and how many group we are having? 4. And we want to compare the increase in weight. Okay. Now you can see that the answer is 46, 44, 44, 27. So this group which have 7 soya meal per week don't have much increase in the weight. And now I have to check the p-value. The p-value is found to be 0.034. Kruskal-Wallis is 8.65. So my conclusion is that the families who eat 7 soya meal per week, they have less or the significantly less increase in weight. So they have the less increase in weight as compared to others. So in this case, in this way we can apply the Kruskal-Wallis test. Okay, now let's move to the one more example. Okay, so we have the data of the publications in a year from the last 3 years. Normally, you know that in the universities there is a performance appraisal, and the professors were asked that how many publications you have in the last 3 years. So we have assistant professor, associate professor, and the professor, and we have the data of their publication in the last 3 years, and we want to check whether the publications is equal or not. So I directly go to the non-parametric test, legacy dialogues, and K independent samples. Publication, go to the test value. Designation, go to the grouping value, and we know that there are 3 groups in the data set. So after assigning 3 groups in the data set, now I am applying Kruskal-Wallis test. Okay. So you can see that the rank of the professor is the least, the rank of the associate professor is the middle, and the rank of the assistant professor is the highest. So higher the rank, higher the publication. So we can say that the assistant professor have the significantly higher publication as compared to the professor. So this way, and it is significant. The difference is found to be significant. So in this way, we can apply the Kruskal-Wallis test. Now we are moving to the last example or last case of non-parametric test, that is known as the Friedman-Hanover test. So the fourth non-parametric test is known as Friedman-Hanover test. This is also the substitute of ANOVA test. Now, and which ANOVA? Because we have seen that the Kruskal-Wallis is also the substitute of ANOVA test. But Friedman is the substitute of related sample or repeated sample ANOVA test, where you are collecting the data from the same respondent but more than 2 times. This data is known as repeated sample data set. Right? So we can Friedman-Hanover is an alternative to one-way ANOVA with repeated measures. Okay. So this is the formula of Friedman-Hanover. This is the null hypothesis, and we are going to the example. Okay. So assume that a faculty decided to teach the students using 3 different methods. So he decided that I will teach chapter number 1 with the help of Blackboard. I will teach chapter number 2 with the PPT, and I will teach the chapter number 3 by case study method. So in this case, students are same, and the faculty teaches the student using the Blackboard, and I didn't measure their feedback. Then the faculty taught next chapter with the PPT, and feedback is measured. And after that, he decided to teach one of the chapter with the help of case study, and this is the feedback. Now he want to know that whether all the teaching methods are equally effective or not. So can we say all the teaching methods are equally effective or not? So for that we want to apply. And why we are moving to the non-parametric? Because sample size in each group is small. And when we apply the one-way ANOVA test, okay, ANOVA, so we can't apply one-way ANOVA on this sample. So we have to arrange the sample another way. So I am going to the non-parametric test, and it is K-related sample. So you can see that we are having the majorly 4 options in the data set. 2 independent, K independent, 2 related, K related. So we are moving to the last K related. And we send all the methods to the test variable. And you can see the test variable here. Friedman is checked. Okay. And the software is telling you the rank of the case study is 3. Rank of the PPT is 1.17. Rank of the Blackboard is 1.83. And the difference is found to be significant. So the conclusion is that case study is more effective because it is having the high rank. And case study of the Blackboard is second, and PPT is the third. So PPT is the most boring method of teaching as compared to case study method, and the case study method is highly effective as compared to other 2 methods, which is shown by the p-value of 0.000. Okay, so in this way we can apply the Friedman-Hanover. Now hypothesis is that there is no difference, and p-value saying that there is a significant difference. So let me show you one more example. Okay. So this is like a experiment. Like for example, if you join a health improvement program or a weight loss program, so your weight is measured in the beginning. Assume that 10 customers, so these are the 10 customers. So these 10 customers join the weight loss program. In the beginning, the weight was this. In the month 1, the weight was this. After the 2 months, the weight was this. So we want to check whether all the participants are able to significantly reduce their weight or not. So analyze dimension reduction, no non-parametric, K related samples. Why related? Because all the participants are same. And just apply. So you can see that initially the weight was less. It increases after 1 month also, and also increases after 2 months. Is this significant? Answer is no. So if you check the p-value, the p-value saying that there is no significant change in the weight. There is no significant change in the weight. Okay, so with this, I closed my session. I decided to teach you 5 non-parametric tests. And all the non-parametric tests I discussed. And if you have any query now, you can ask.
Let's have some queries or questions to ask you. Shall we proceed to queries? Ask queries, sir?
Yes, sir.
Shall we proceed?
Yeah.
Okay. So what are the first query? What are category?
Yes, sir, please.
What are categorical variables?
What are categorical variables? The nominal variables are categorical variables, like male and female, like married and unmarried, like low income, high income. So they are known as categorical or non-nominal variables.
About the chi-square test.
Yep. Any other query, please? Okay. So there are a lot of queries here. Let me check.
Slow connection. The problem is we are getting this problem. Can you hear the second query, sir? What should be the data format for the chi-square test?
What is the data format for chi-square test?
Yes, sir. Yes.
Actually, the data must be categorical in nature. So I told you that the chi-square test is only applicable when you have only the nominal variables. Or nominal variables are represented by the codes, like 1 for male, 2 for female, like 1 for drug, 2 for alcohol. So we have the categorical variables in the data set.
Okay, okay, sir. So following on, we have one more query. What do you mean by p-value?
P-value?
Yes, sir.
Okay. So p-value is the probability of committing error number 1. It is a probability of committing type 1 error. Or in there are two meanings of p-value. It is as per the level of significance. The level of significance, the p-value is showing you the probability of committing type 1 error. But when we do a hypothesis testing, the p-value will tell you whether your sample lies in the rejection region or the acceptance region. If p-value is less than 0.05, it means your sample is lying in the rejection region. Null hypothesis can be rejected on the basis of this p-value concept.
Okay. Okay, sir. Okay. So now we move to the last query of this session. That is, in case where sample size is large, that is 4 to 500 or above, and the data is abnormal. In this case, which kind of test should be taken?
Basically, if the sample size is large and data is not normal, it means you selected a wrong scale to collect the data. This indicates that the scales which you are using to collect the data is wrong. So you have to correct the scale rather than changing the test. Because the central limit theorem say that if you increase the sample size, the data should be normally distributed. So basically, what you are saying that I'm using the large data, but it is not normal. It means your scale is wrong. Or there is one more possibility. Sometimes what happens that because of the increase in the mean, the kurtosis is very high. So in that case, you have to check whether the kurtosis is a problem or the skewness is a problem. If skewness is a problem, that really it is not a normal distribution data. But if skewness is fine, but kurtosis is a problem, then you can ignore it, because kurtosis means symmetrical data, symmetrical distribution, and most of the financial data is kurtosis, and we treat it as a normally distributed data.
Okay, sir. Okay, sir. Thank you. Thank you for entertaining all the. Now, sir, I like to share the certificate of appreciation given by the organizing committee to you as a token of love and respect. Sir, here is it.
Thank you, sir.
Most welcome. This, we have come to the end of today's session. So now, on behalf of University Lucknow, first of all, I would like to extend a heartiest word of thanks to our Chancellor, Honorable Chancellor and Founder, Professor Syed Wasim Akhtar sir. Program. A sincere thanks to our Honorable Pro-Chancellor, Professor Nadeem Akhtar sir, for his regular guidance and support. I would also like to thank to our Honorable Vice Chancellor, Professor Javed Musarrat, for his blessings and always inspiring us to conduct such programs. I am thankful to our guest speaker of this session, Professor Ajay Kumar Chauhan sir, for sparing his valuable time and such a remarkable session. I hope the audience must enjoy and learn a lot from this session. In a final footnote, I would like to thank our team of the department, Professor A.K. Saxena, and head of the department, Dr. Syed Shahid Mazhar, for believing on me and giving me this opportunity to moderate this session. Now, last but not the least, I would also like to extend a heartfelt thank to all the faculty members, research scholars, and their participants actively participate. Once again, thank to all of you. Thanks to all of you.